Continuing on, we're going to look at section 9B, which is linear modeling. So mostly in this section, we're going to talk about slope and slope-intercept form. It says a linear function has a constant rate of change, and it is a straight line graph. The rate of change is equal to the slope. So if I ask you to find the slope, you're finding the rate of change. If I ask you to find the rate of change, you're actually just finding the slope. The greater the rate of change, the steeper the slope. And you can calculate the rate of change by finding the slope between any 2 points on a graph. The rate of change is equal to the slope, which is equal to the change in the dependent variable over the change in the independent variable. Now, you've always seen this as written y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And that's still true. If you can remember that, great. I think it's a little bit easier to remember change in the dependent over change in the independent. Or sometimes I'll just say subtract the y's over subtract the x's. But whatever's simplest for you. If you have a line graphed, then to find the slope of the line, you're finding the change in the dependent variable, or the rise, over the change in the independent variable, the x values, the run. Example 1 says, a small store sells fresh pineapples. Based on data for pineapple prices between $2 and $5, the store owners created a model in which a linear function is used to describe the demand. The number of pineapples sold per day is the demand. And that varies with the price. For example, the point $2.80 pineapples means that at a price of $2 per pineapple, 80 pineapples can be sold on an average day. What is the rate of change for this function, and discuss the validity? So here's our graph, and we see if the pineapples are $2 a piece, then we'd sell 80 of them. And there's another point on here. If the pineapples are $5 a piece, we'd sell 50. So you can see if the price of the pineapples goes up, the number sold goes down, which makes sense, okay? Would you be more likely to buy a $2 pineapple or a $5 pineapple? Probably a $2 one, unless you're really desperate for a pineapple. Okay, so we're asked to find the rate of change. We've got 2 points. We've got the point 280 and the point 550. So to find the rate of change, which we'll sometimes say is m for the slope, we take the y values subtracted. So I'm going to say 50 minus 80. I usually start with the second point just because of that's what I've always done. And then subtract the x values, so 5 minus 2. You just have to make sure you start with the same point on the top and bottom. So we get negative 30 over 3, which reduces to negative 10. Now, what is that saying, though? Okay? I'll move this over. What does the negative 10 mean? Well, if you go back and you put in your units for the independent and dependent variables, then it would help us to understand what negative 10 means, okay? On the top was your y values, your independent variable, and there we were talking about the y values were the pineapples. On the bottom, there's a 1, of course, and the independent variable were the price in dollars. So there's that. So what does this say then? Negative 10 pineapples for $1. Basically, the number of pineapples sold. The negative says it decreases or decreased by 10 for every $1 increase. So every time the price went up by $1, you're selling 10 less pineapples, which kind of makes sense. Now, it asks us to discuss the validity of the model. Well, when we discuss validity, we want to look at the points where it crosses the X and Y axis. So, looking at this point down here, that's saying that if the pineapples are $10, you'll sell no pineapples. Well, that kind of makes sense, okay? That would be an expensive pineapple. And I know I'd be very unlikely that I would pay $10 for a pineapple. If we look at where it crosses the y-axis, that's saying that if the price of pineapples was $0, so basically if they're free, then you'd sell 100. Okay. Yeah, if there's only 100 pineapples available, but if there were more, let's say there were 500 pineapples, if they were free, wouldn't they end up getting rid of all of them? Most likely. So there's other variables that come into play, but regardless, this function is a pretty good representation of the demand of pineapples. Rate of change rule. It says it allows us to calculate the change in the dependent variable from the change in the independent variable. So we say that the change in the dependent variable is equal to the rate of change times the change in the independent variable. Just to take it back to something you might have seen before, and we're not going to use this, so don't worry about writing it down. But what this is saying is the change in the dependent variable, that's y sub 2 minus y sub 1, equals the rate of change, m, times the change in the independent variable, x sub 2 minus x sub 1. So that might look very familiar. That's point slope form. No. Yes, point slope form. Okay? And again, we're not going to talk about point slope form, but just trying to take it back to the fact that you have seen this before. Example 2 says use the linear demand function and predict the change in demand for pineapples if the price increases by $3. So it says the change in the dependent variable. So we're looking at the change in demand is equal to, I have to move that down, the rate of change times the change in the independent variable. That was the price. So the change in the price. Okay? So the change in demand is equal to the rate of change. We found that to be negative 10 times the change in the price was increasing by $3, so positive 3. That gives us negative 30. Negative 30 pineapples. Now, obviously, you can't have a negative number of pineapples. What the negative is indicating is that if you increase your price by $3, you're going to sell 30 less pineapples. And I'm going to go up here and write that. So the demand, if we increase the price by $3, will decrease by 30 pineapples. The equation of a line, y equals mx plus b. Well, that's not really in that order there. But the equation for a linear function is the dependent variable, that's y, is equal to your initial value, that's what we've always called b, plus the rate of change, we've called m, times the independent variable, x. So b plus mx, same thing as mx plus b. And here it is. For example, if we look at this line, y equals 4x minus 4, it has a slope of 4. And a y-intercept of negative 4. And to graph this line, we graph the y-intercept first, negative 4 on the y-axis. It's the y-intercept because that's where it crosses the y-axis. And then we would rise 4, and there's an imaginary 1 on the bottom, so run 1. So rise 4, run 1, and then we can draw our line. This is just telling you if the slope is positive, the line's going to go up to the right. If the slope is negative, it's going to go down to the right. And if the slope is 0, well, it's not going to go up or down. It's just going to be horizontal. If you vary the intercept, it just moves the line up and down. And it creates parallel lines. So the slopes are the same. You'll have a parallel line. The y-intercept just moves it up or down the y-axis. Example 3 says, use the function shown to the right to write an equation that describes the rain depth at any time after the storm began. Okay? So we want to write an equation. We need to find m and b. Ooh, I don't have much space, do I? So m, well, let's find b first. B is the initial point where it's starting, and it's starting here at 0. So B is just 0. M is the rise over run, which they've already found for us here. So if we took 2 points and went up and over, then that's going to tell us what the slope is, which they said is 0.5. So the equation of our line would be, in y equals mx plus b form, y equals 0.5x, and we don't need to write plus 0. Then it asks us, use the equation to find the rain depth 4 hours after the storm began. So we just plug in. Y equals 0.5 times 4. 2. The depth of the rain after 4 hours would be 2 inches. Okay, and lastly, we're going to look at creating a linear function from two data points. So let's say you're given 2 points. You can find the slope, and you can use those points to find the y-intercept. Then you can write your equation in y-intercept form. So these are the steps if you ever need to look back at them. Example 4 says, until about 1850, humans used so little crude oil, then we can call the amount 0. Now, crude oil, what are they talking about? Like gas or oil to heat your house, that type of thing. So before 1850, there weren't cars, so you didn't have to worry about gasoline. People didn't heat their house with oil, so you didn't have to worry about that. So, we can pretty much say that the amount of oil used was 0. At least in comparison to the amount used since that time. By 1960, humans had used a total of 600 billion cubic meters of oil. That's a lot. Create a linear model that describes world oil use since 1850. So, what we want to start with is our 2 points. So in 1850, it says we used 0 oil, or at least that's our assumption. So our first point would be 1850, 0. The second point is it says by 1960, we'd use 600 billion cubic meters. So the second point can be 1960, 600. Realizing that 600 means 600 billion, not just 600. Create a linear model. Okay, we can do that. First, find the slope. So the slope would be the y values subtract the x's. So 600 minus 0 over 1960 minus 1850. That's 600 over 110. Or if we change that into a decimal, 5.45. What does that mean? That means 5.45 billion cubic meters of oil per year. So on average, since 1850, we've used 5.45 billion cubic meters of oil per year. That's probably not very accurate because we started out using less and now we're using more. So probably more exponential, but we'll talk about that next chapter. Okay, so we've got that M is 5.45. And we've still got our 2 points, 1850, 0, and 1960, 600. Now we want to find B, okay? And in order to find B, if you remember how to use point slope form, you can do that. I usually go with this method. Use your y equals mx plus b. Plug in for m. And choose one of the points to plug in for y and x. So I'm just going to use the first point because it has a 0 in it, so that makes it easy. So y is 0, x is 1850. And we finish solving. So we'd have 0 equals 5.45 times 1850 is 10,083. And then to finish solving this, subtract 10,083 from both sides. So B is negative 10,083. Now we can write the equation of our line then. Excuse me, I'm changing colors. Okay, so Y equals, M was 5.45, X plus B, which it's negative, so we won't worry about the plus, minus 10,083. So there's our equation. It says also discuss the validity. Again, I think it's highly unlikely that we've used an average of 5.45 over time or per year starting at the beginning. It's most likely we use less to start with and more now. And if we look at this graph over here somewhere, there it is, you can see the pink one is our equation. Y equals 5.45x minus 10,085. 3. While the blue one is an exponential function, where we started out using less and we're using more and more over time. So, yeah, it's more likely that this is exponential than linear, but linear gives us a good idea anyway. And we'll talk more, as I said, about exponential in the next chapter. And so that concludes this section and today's lessons. That also concludes this chapter. We'll spend Wednesday doing a review. I guess you'll do that on your own. I'll have the solutions to the review in Moodle for you. So you'll have your review in Moodle and the solutions will be there. You'll also have a review you can do in my math lab if you like. And let's see. So your test won't be due until next Tuesday, April 7th. The 9A and 9B homework will be due on April 5th. And the 9A lab, you just got a lab for 9A. You might have one for 9B too. Watch Moodle. And then, like I said, your test isn't due until April 7th. But I would, if I were you, I'd do the test before we start the next section on April 6th. As usual, call me or email me if you have any questions, especially about the review or anything else. Just let me know. And hang in there.